Hello, and welcome to video lecture number 6, which covers section 1.4, day 1, functions. Please take a moment, as always, to read today's objectives. We begin this lesson by defining the concept of a function, and in all of mathematics, there is probably no larger concept and more useful concept than the function. So, no matter which class you're in, Algebra 1, Algebra 2, Geometry, you'll see functions all over the place, and you'll continue to review that concept, and that's why we're doing it here. So the function is a relation from a set A, called the domain, to a set B, called the range, such that each element x in the first set A is assigned to exactly one element y in set B. Now, I'll admit that definition is rather lengthy and it can be somewhat confusing. So there are some diagrams below that we will use to help us understand this a little bit better. So to give you a better idea of what a function is, I have two visuals split down the middle by this black line. Let's focus first on the one on the left. What is a relationship that can be a function? So I've given you one example here. So let's suppose our set A contains the different or various times of day, and I've just listed a few here. So like 1 a.m., 2 a.m., 3 a.m. on the left. And then in the range, our set B is going to contain temperatures at those specific times. To show inputs being related to outputs, we will use arrows. So let's suppose that at 1 a.m. it was 58 degrees. Let's suppose that at 5 a.m. it was 64 degrees. Let's say at 6 a.m. it was 67 degrees. And how about maybe at 2 it was also 58 degrees. At 3 a.m. maybe it was 62, and maybe at 4 it was also 62. So the arrows represent the function that takes the values in set A and brings them to set B. Now realize that we do have multiple x's going to the same y, but if you look closely at the definition, that still is a function. So the relationship of the time of day versus the temperature would constitute a relationship that is a function. Now let's take a look at something that isn't a function. So if you look on the right, we have the inputs in set A related to the shoe size and the outputs being the number of pets. So let's suppose that someone has a shoe size of 8 and they have 0 pets. But there is another person who also has a shoe size of 8 and they have 4 pets at home. So when you see this arrow, double arrow, coming from the same number in the domain going to two different y values, that's not a function. So if we look at these in terms of ordered pairs, we would have 8, 0 and 8, 4. Since we have one x going to two different y values, that is not a function. And moreover, if you were to graph these 2 points, you would hopefully notice that they lie directly above one another. When this happens, that is also an indication that the relationship is not a function. So when you write equations as functions, you use a notation that's special so we can identify already that the equation is a function. So what you'll see are 3 columns. First column has input variables, the second column has our outputs, and then the third column are example equations, all using what we call function notation. The most common one, obviously, is the f of x, f standing for function. So if you're to see something like f of x equals 1 minus x squared, there is no question it is a function because it uses the f of x notation, so we will never have to determine whether something like that is a function when it's written that way. No longer are you going to see y equals. A lot of times now it is replaced with f of x going forward. So you need to get used to this notation, and every time we don't just use f of x, sometimes we may use a g for the function or a c or anything at all, but most commonly the f for function. If you're asked to determine whether a relationship is a function and you have a graph, you can use the vertical line test, and we'll talk in just a moment on how to use that test if you don't already know. If you're asked to determine whether a relationship is a function and you have an equation or a table and not its graph, then the best way to do that is to decide whether each input is matched with exactly one output. That is basically the definition of a function. So clearly, it's a little more difficult to determine whether an equation or a table is a function. You have to use a lot more thought than so if you have a graph. So we'll provide some practice in the upcoming examples to determine whether various relationships are functions. We mentioned previously the vertical line test. So what is it if you don't already know? Basically, if you run a vertical line over the graph and your vertical line touches it in more than one spot simultaneously, then the graph and the relationship is not a function. There will be more examples to come that demonstrate using the vertical line test. As referenced previously, the domain then is the set of all input values of a function, and typically the input values or variables are x's, although we don't always use x's in our equations. Input values are also known as control or independent. So all three words I've underlined are synonymous with each other, and you should know that all three words can be used interchangeably. The range is the set of all output values of a function, and typically we use y to represent the range. However, we can use other variables. So once again, we call them output. You may also hear the y or the range referred to as the dependent variables. As you probably may already have recognized, functions can be represented in four ways. The first way a function can be represented is verbally, and by that we mean a sentence using words. The second way is numerically, and this means either a table of values or a series of ordered pairs. Thirdly, functions can be represented graphically, and those obviously are points plotted on the Cartesian plane and generally connected with a smooth curve. Finally, functions can be represented algebraically, and by that we mean using equations. Example 1 is associated with objectives number 1 and 2 from this lesson and asks you to determine whether each verbal, numeric, or graphical relationship is a function. If you say yes, you must give the domain. If you say no, we don't need to apply the term domain because it, again, only corresponds to functions. So I'll pick one at random here to try. We'll try B, and this is a numeric relationship or a table, and we don't have a graph, so we can't use the vertical line test. I suppose you could graph this if you wanted, but we should be able just to look at it and tell. Observe that each x value, 1, 2, 3, or 4 people, all correspond to its own unique y value. So this is an indication that, yes, this is a function. So now we have to write our answer, explain it, and give the domain. So as you see, my answer or explanation is yes, and due to the fact that each x has exactly one y value. Below, you will see first my domain on the left and then my range on the right, and notice because I cannot have continuous or decimal number of people, I have to write each domain value separately in a set form. So notice I have 1, 2, 3, 4. The same will go for the range. You don't always write the domain and range this way, but in this case we are forced to. Next, I will try example 1e. Now, this is a graphical relationship, so a nice easy way to determine whether this is a function is to use the vertical line test. Notice that any vertical line I happen to run across this graph no matter where the vertical line is located, I will only touch the graph in one spot. This is an indication that this graph is a function. Your explanations for graphs can be pretty straightforward. You either simply say passes the vertical line test if it is a function, or you say fails the vertical line test if it is not. This one is, so I've said passes the vertical line test. Now I must find its domain and range. Since this graph is a function, we were asked to find its domain, and notice I've highlighted in blue. When I look at the domain, I want to scan the graph from left to right because domain refers to the set of all x's, so I want to look parallel with the x-axis. Notice that the graph continues to the left and to the right forever as indicated by its arrows. So the far left, we have negative infinity, and on the far right, we have positive infinity. Now, the sideways 8s are the symbols that we will use for those. So how do we write our domain? So if you look what I've boxed, you could write the domain in one or two ways. The first way is how you've probably already done it in your algebra classes. We use greater than or less than symbols, x in the middle because we're talking about domain. And notice I have x greater than negative infinity and less than infinity. Now, not equal to. There are no equal to signs here because we can never technically touch or reach negative infinity or positive infinity. The one on the right is the most commonly used way to write it outside of algebra. So when you start to take pre-calculus and calculus, you'll start to see the domain written this way, and it almost looks like an ordered pair. However, it's not. What goes on the left is the minimum x value that is used. Well, in this case, it's negative infinity. What's on the right is the maximum x value used, and that is positive infinity. And the parentheses here actually have significance. And since they're rounded parentheses, that is an indication that we are not equal to those. So clearly, right, we don't have equal to signs underneath the greater than and less than symbols. So that's why the parentheses are rounded. If we are equal to, they will be brackets. And we will do several examples of these in class to help you better understand. The last example I would like to show you is a verbal representation, and it says the number of representatives from a state constitute our domain or our x values, and the number of state senators represents our y values. Now, to do this problem, it may require a little background knowledge about civics. So on the left, the number of state representatives. So depending on how populated a state is, it will have a certain number of state representatives. So the smaller populated states like Vermont or Rhode Island or Wyoming may only have one state representative, while larger states, more populated states like California, has the highest number of state representatives at 53. However, no matter the size or population of a state, each state only has 2 state senators. So if you look at the map, no matter what the number of x's are, we're always going to have 2 state senators. So if you were to look at these points on a graph, they would indeed pass that vertical line test. Now notice I don't have a single x going to 2 separate y values. Every single x will go to 2, and indeed this is a function. So now let's find the domain. So my explanation is, yes, this is a function, and because each x maps to the same y value of 2, it indeed is a function. Now the domain would correspond to the values of the state representatives. And since I can't have decimal values for number of state representatives, we must list them in a set. So remember, 1 is the smallest number of state representatives for the smaller, less populated states, and 53 is the number of representatives in California. Now, not every single number is used between them, but to make it a little more easy, I'll just put in the ... and go to 53. Please take a moment to pause the video and try the remaining exercises from example 1 that I have not shown you, and we will check them in class tomorrow. Example 2 gives us some algebraic relationships and asks us to determine whether they are functions. Of course, we will have to explain our answers, And if we say yes, we must give the domain. So I'll try example 2C, and I ask that you do A and B on your own and check them tomorrow. So the easiest way, in my opinion, to determine, well, whether equations are functions is to graph them, because generally graphing and using the vertical line test is the easiest way to determine a function. So if you take a look at the sketch of the graph I've drawn, this equation represents a quadratic. All quadratics pass the vertical line test. Again, my vertical lines only touch the graph at one spot at a time. So indeed, this is a function. So now let's write our answer and explanation. So my explanation is pretty straightforward. Since I graphed it, I will say yes because the graph passes the vertical line test. And if you look for its domain, the ends of the parabola will extend out to the left and out to the right forever. So our domain, once again, will be written, similar to a previous example, as parentheses, negative infinity, comma, positive infinity. And I want you to get in the habit of writing the domain this way because, again, this is the more commonly used version once you get past Algebra 2. So again, please try examples 2A and B on your own, and we will check them tomorrow. Part 3 of your Section 1-4 Day 1 notes correspond to objective number 3, which is evaluating functions. So in example 3, you're given one function and you're asked to evaluate the function at the given values. Well, there is no need to determine whether this is a function because it uses the notation f of x. So that's an automatic indicator it is a function. So I'll try example 3c with you. And f of x minus 1, as you look at my note, simply means that we're going to substitute x minus 1 everywhere we see an x in the function. So I will write f of x minus 1 equals 10 minus 3 times x minus 1 squared. From here, we will just try to simplify the right side as much as we can, and then we will be all done. So I went ahead and showed you multiple steps of the simplification needed to get us to our final answer. Notice at this stage, one of the most common mistakes is that we'll take the 2 and we'll want to distribute the exponent to both inside. Well, remember, x minus 1 squared actually means you need to write it twice, and then we need to use what we call FOIL, which is simply an acronym that tells us or reminds us that we need to use the distributive property twice, meaning I need to take x and multiply it by both things in the other parentheses, and I need to take negative 1 and multiply it both things in the other parentheses. So as I continue on, you will see that after I multiply and combine all like terms, our final answer would be f of x minus 1 equals negative 3x squared plus 6x plus 7. So please try examples 3A and B on your own and have them ready to check in class tomorrow. Example 4 introduces you to a piecewise function. So a piecewise function is, as its name suggests, a graph that looks like it has multiple pieces, and those multiple pieces come from multiple equations. So yes, a function can have multiple equations incorporated into it. And notice I've labeled for you the first equation, which is listed on top. Its domain is listed next to it. And then equation number 2, x minus 1, is on the bottom. So if you're asked to evaluate a piecewise function, you have to pay attention to the domains. So notice that for letter 4a, the x value we're asked to substitute is negative 2. Well, clearly, negative 2 is less than 0. Since it's less than 0, that means that I'm going to use the first equation because that's the only equation we can use when x values are less than 0. So to evaluate f of negative 2, we will simply plug in the negative 2 in for x in only the top equation. The bottom one is not valid in this case. So simplify and we have our final answer. When you simplify, you end up getting f of negative 2 equals 5. Well, remember that the number inside the parentheses is our x, and our output is 5, or the y. So you may be more familiar with writing it as an ordered pair. But either way, we have the same answer. So this concludes video lecture number 6. Please take a moment to look back over your notes and come up with at least one question you have that you can pose in class tomorrow. Thank you for watching, and good luck.